Discover 3 counterintuitive cooking principles that explain why wet foods brown, salt makes meat juicier, and searing doesn't seal juices. Cooking is full of paradoxes where intuition fails, and science reveals surprising truths about moisture, flavor, and texture. Let's start with the first paradox. The Maillard reaction needs heat and low water activity to create delicious browning. Surface water caps temperature near 100 degrees Celsius and quenches the chemical pathways that create browning. A wet surface stays near boiling temperature, preventing the higher temperatures needed for browning reactions. The key is reducing water activity. As water activity decreases, browning reactions can proceed. Several techniques help remove or bind surface water to enable browning. First, rapid evaporation through high heat contact removes surface moisture quickly. Second, pre-salting initially draws out water, then the salt solution is reabsorbed, concentrating surface solutes. Third, cast iron pans store tremendous heat, enabling rapid evaporation at the contact surface. Cast iron transfers intense heat to the food surface, driving off moisture rapidly and enabling deep browning. The trick is staging. First, dehydrate the surface fast, then let the Maillard reaction proceed at higher temperatures. The process flows from wet surface through rapid drying to beautiful browning. Patting a steak dry before searing produces a deep crust that a damp steak never attains. The second paradox reveals how salt initially dehydrates meat to ultimately make it juicier. When you first salt meat, osmosis pulls moisture from muscle cells, seemingly dehydrating the tissue. Osmotic pressure draws water molecules out of the meat tissue toward the salty exterior. But then something remarkable happens. Salt ions dissociate proteins, which then swell and hold more water than before. After minutes to hours, that salty brine solution is reabsorbed as chloride ions weaken protein bonds. Chloride weakens electrostatic bonds in myofibrillar proteins, especially myosin, creating space for both water and salt. Protein fibers transform from tight bundles to swollen structures with space for water molecules, increasing overall juiciness. This creates the paradox. A short-term water loss yields a larger long-term gain in moisture retention. Timing and salt concentration are critical. Too strong or too brief can over-tighten proteins or simply desiccate the meat. A properly dry-brined chicken at 1 to 1.5% salt by weight overnight loses a little drip early but roasts significantly moister than an unbrined bird. The third paradox debunks the old myth that searing seals in moisture. The traditional chef's wisdom says that searing creates a seal that locks moisture inside the meat. But measurements show seared meat often loses more water because higher surface temperatures tighten and rupture muscle fibers. High heat causes fiber shrinkage and rupture, actually expelling more moisture rather than sealing it in. Above 60 degrees Celsius, proteins shrink longitudinally, squeezing out water. Above 70 degrees Celsius, transverse shrinkage further compresses fibers and expels even more moisture. What searing truly accomplishes is building a deeply flavorful, hydrophobic crust rich in Maillard reaction products. For maximum moisture retention with great flavor, use the reverse sear method. Start low to gently set proteins, then finish hot to create the crust. The reverse sear sequence cooks meat gently at low temperature first, then applies a brief high heat finish for crust development. 2 steaks cooked to equal doneness. The reverse seared one weighs more after cooking yet tastes just as brown due to the late, brief, high heat finish. The key insight is that increased flavor from searing does not imply decreased moisture loss. These are independent factors. Let's review the 3 counterintuitive principles we've explored. First, browning requires removing surface water through rapid evaporation or water binding to enable high-temperature Maillard reactions. Second, salt initially dehydrates meat through osmosis, but ultimately increases water holding capacity by dissociating proteins. Third, searing creates delicious flavor through crust development, but does not physically seal moisture inside the meat. Understanding the science behind these paradoxes transforms cooking from guesswork into precise control of moisture, flavor, and texture. Explore 3 mind-bending paradoxes that revolutionize how we understand cooking. Today, we dive into the fascinating chemistry behind 3 cooking paradoxes that challenge conventional wisdom. Our first paradox reveals why browning requires both heat and the absence of surface water. The Maillard reaction is the chemical process that creates those delicious brown crusts on our food. However, surface water is the enemy of browning because it caps temperature near 100 degrees Celsius. When surface water is abundant, heat cannot raise the temperature high enough for Maillard reactions to occur effectively. The solution to this paradox is to dehydrate the surface rapidly before browning begins. By removing surface moisture first through evaporation or heat, we create conditions perfect for Maillard browning. Effective techniques include patting food dry using preheated cast iron pans and employing air fryers with forced convection. The formula is simple. High heat plus a dry surface equals a perfect brown crust. A patted dry steak develops a deep, flavorful crust, while a damp one remains pale and steams instead of browns. Our second paradox shows how removing water initially leads to juicier results later. When you salt meat, osmosis initially pulls moisture from the muscle tissue outward. Salt crystals on the surface draw water molecules outward, seemingly dehydrating the meat. But hours later, that salty brine re-enters the muscle as salt ions dissociate and modify proteins. The salt-enriched brine flows back in, and proteins restructure to hold more water than before. Salt ions weaken protein bonds, causing myosin to swell and create space for additional moisture. The equation is salt out plus time leads to salt in plus juicier meat. For best results, use 1 to 1.5% salt by weight and let it work overnight for a dry brine. A dry brine chicken retains significantly more moisture after cooking compared to an unsalted bird. Our final paradox debunks the myth that searing seals in moisture. The old culinary myth claimed that searing creates a seal that traps juices inside the meat. In reality, measurements show that seared meat can actually lose more water due to higher surface temperatures. High heat tightens and ruptures muscle fibers, potentially releasing more liquid than gentle cooking. What searing actually does brilliantly is create a hydrophobic, flavor-packed Maillard crust. This crust is packed with hundreds of flavor compounds that make the meat taste richer and more complex. For maximum moisture retention with great flavor, use the reverse sear method. Start with low heat to cook gently, then finish with a brief high-heat sear for the crust. The key insight is that increased flavor does not require decreased moisture. A reverse-seared steak retains more weight and moisture while achieving the same delicious brown crust. Let us summarize these 3 fascinating cooking paradoxes. First, you must dry the surface of wet foods to enable the Maillard browning reaction. Second, removing water initially with salt leads to greater juiciness after proteins restructure. Third, searing creates incredible flavor through Maillard reactions, but does not seal in juices as once believed. Understanding these paradoxes empowers you to cook with scientific precision and achieve restaurant-quality results at home. Discover how low temperatures and long cooking times transform tough cuts into tender, succulent masterpieces. Tough cuts contain collagen fibers that need careful temperature control to transform into tender, juicy meals. Let's explore why cooking low and slow makes tough cuts tender. The magic happens between 60 and 75 degrees Celsius, where collagen transforms without drying out muscle fibers. This graph shows how collagen toughness drops dramatically in the 60 to 70 degree range, our ideal cooking zone. At these temperatures, tough collagen slowly hydrolyzes and transforms into smooth, lubricating gelatin. But muscle fibers start to dry out and tighten if we go much above 70 to 75 degrees. Collagen's rigid rope-like structure breaks down into smooth gelatin molecules that lubricate and moisten the meat. The counterintuitive solution is to cook at modest temperatures for extended periods. Low temperature plus long time equals both tender and moist results. Moist environments like braises or sealed bags prevent water loss and accelerate collagen's chemical transformation. In a braise, water molecules surround the meat, enabling collagen breakdown while preventing moisture loss. Let's compare 2 ways to cook the same chuck roast and see the dramatic difference. At 68 to 72 degrees for 12 to 18 hours, the roast becomes silky tender. At 90 degrees for 3 hours, it dries out and frays. The gelatin produced lubricates the meat and thickens cooking juices, amplifying that moist, succulent sensation. When you remove meat from heat, two seemingly contradictory things happen simultaneously. Heat continues flowing inward from hot outer layers, raising the core temperature by a few degrees even off the heat. Heat flows from the hot exterior inward toward the cooler center, continuing to cook the meat even after removing from heat. The core temperature typically rises 3 to 5 degrees Celsius during the rest period. At the same time, internal pressure falls, and juices that were squeezed out redistribute back into the muscle fibers. Juices that pooled outside the fibers during cooking flow back in, making the meat moister when you finally cut it. If you cut immediately, you release that internal pressure, and all those juices spill out onto the cutting board. A 1.5 kilogram beef roast should rest about 20 minutes, during which it rises 3 to 5 degrees and retains far more juice. Dried beans present their own chemical puzzle involving acids, alkalis, and cell wall structure. Bean cell walls contain pectin and hemicelluloses that determine texture and cooking time. Adding alkali like baking soda accelerates softening by breaking down pectin, but too much creates mushy, soapy beans. Baking soda gives you speed, but threatens to turn beans to mush. Alkali moves beans from firm to perfect quickly, but cross the line and you get unappetizing mush. Acids like tomato or vinegar stabilize pectin, keeping beans intact but requiring longer cooking times. Acid gives you firm texture, but demands patience. Chili with tomatoes keeps beans firm for hours, while a tiny pinch of baking soda in hummus water cuts cook time dramatically. Salt was once blamed for tough beans, but actually helps skins hydrate evenly and prevents bursting. Let's recap these cooking science principles. Cooking low between 60 and 75 degrees for extended time transforms tough collagen into tender gelatin. Resting allows carryover cooking while pressure drops and juices redistribute back into the meat. Beans soften based on pH. Alkali speeds softening but risks mush, while acid preserves shape but extends time. Understanding these chemical principles lets you control temperature and time to achieve exactly the texture you want. Explore 3 fascinating paradoxes that challenge our assumptions about cooking. Today we examine 3 counterintuitive phenomena: how water affects chocolate, why bread stales differently at different temperatures, and how pressure cooking can be gentler despite higher heat. Why does a drop of water ruin melted chocolate, but lots of water saves it? Melted chocolate starts as a smooth, fat-continuous suspension where cocoa butter surrounds sugar and cocoa particles. Add a tiny amount of water and the chocolate seizes into a grainy, clumpy mess that won't flow. When you add just a drop of water, it wets a few sugar crystals on the surface, forming a sticky syrup. This syrup acts like glue, dragging fine cocoa particles into ugly clumps that lock up the mixture. The water droplet creates zones of syrup that pull particles together, causing the dreaded seizing effect. However, if you add a lot of water or cream, something magical happens. With enough liquid, you flip from a fat continuous to a water continuous emulsion, where fat droplets disperse smoothly. This creates ganache, a glossy, pourable sauce, where chocolate fat droplets float in water, stabilized by lecithin. So paradoxically, a teaspoon of water destroys a bowl of chocolate, but a full cup transforms it into silky ganache. A few drops create sticky mud that locks everything up into grainy clumps. But plenty of water creates a smooth, pourable slurry where everything flows freely. Why does bread go stale faster in the fridge than at room temperature, but slower in the freezer? Fresh bread has a soft, springy crumb thanks to starch molecules in an amorphous, flexible state. Staling happens when starch chains, especially amylopectin, recrystallize and expel water from the bread structure. As these chains reorganize into crystals, the crumb firms up and becomes dry and leathery. In fresh bread, starch chains are loosely arranged and flexible, holding water in the structure. During staling, chains align into rigid crystals that squeeze out water, making the bread hard. The fridge temperature of 0 to 5 degrees Celsius is actually the worst range for bread storage. This cool zone accelerates starch crystallization, making your baguette leathery overnight even